Welcome to Session 5, Histograms and Distribution Shape. A histogram groups numerical measurements into non-overlapping intervals, so its bars touch. It reveals where values concentrate and whether a distribution is symmetric, skewed, clustered, separated by a gap, or shaped by the choice of bin width. 10 real-life examples will help you total bin frequencies, identify a modal interval, calculate a percent within a bin, name skew by the tail direction, define unambiguous boundaries, and compare reliability as well as center. Example 1. A commute histogram has bins 0 to 9, 10 to 19, 20 to 29, and 30 to 39 minutes with frequencies 3, 8, 11, and 4. How many commuters are represented? Plan. Add the frequencies across all non-overlapping bins. Step 1. List the bin counts 3, 8, 11, and 4. Step 2. Compute 3 plus 8 plus 11 plus 4 equals 26. Step 3. Every commuter belongs to exactly one bin. Step 4. The histogram represents 26 commuters. Quick check. The sum of all bar heights must equal the sample size. This matters in real life because transit studies group continuous travel times to reveal overall patterns. Example 2. Using the same histogram, identify the modal interval. Plan. Find the interval with the greatest frequency, not an exact individual value. Step 1. Compare the frequencies 3, 8, 11, and 4. Step 2. The largest frequency is 11. Step 3. That frequency belongs to the 20 to 29 minute bin. Step 4. The modal interval is 20 to 29 minutes. Quick check. A histogram cannot tell which exact minute within 20 to 29 occurred most often. This matters in real life because the busiest travel time interval helps planners target congestion reduction. Example 3. A histogram of 40 delivery times shows 14 times in the 30 to 39 minute bin. What percent fall in that bin? Plan. Divide the bin frequency by the total number of observations. Step 1. The bin frequency is 14. Step 2. The sample size is 40. Step 3. Compute 14 divided by 40 equals 0.35. Step 4. Convert to 35% of deliveries. Quick check. Multiplying 40 by 35% returns 14. This matters in real life because operations teams compare percent in bin targets across weeks with different order totals. Example 4. Income data have many middle-income households and a few extremely high-income households. Predict the histogram shape. Plan. Locate where most values lie and identify the direction of the extreme tail. Step 1. Most households lie in low or middle income intervals. Step 2. A few values extend far toward larger incomes. Step 3. The long tail points to the right. Step 4. The distribution is skewed, right? Quick check. Skew is named for the tail direction, not the side containing most observations. This matters in real life because income reports often use medians because a right-skewed tail can pull the mean upward. Example 5. A retirement age histogram contains many values near 65 and a few much lower ages caused by early retirement. Predict the shape. Plan. Identify the main concentration and the direction of the sparse extreme values. Step 1. Most values cluster near the higher age of 65. Step 2. A few early retirements extend toward lower ages. Step 3. The longer tail points left. Step 4. The distribution is skewed left. Quick check. A left tail means skewed left, even though the tallest bars are on the right. This matters in real life because pension planners study the full distribution rather than relying only on a typical retirement age. Example 6. A production process has measurements centered near 50, with bar heights that fall similarly on both sides. Describe the shape. Plan. Compare the left and right sides around the apparent center. Step 1. The highest frequencies are near 50. Step 2. Frequencies decrease as values move away from 50. Step 3. The left and right patterns are approximately mirror images. Step 4. The distribution is approximately symmetric and centered near 50. Quick check. Symmetric does not mean every paired bar must be exactly equal. Small sample variation is normal. This matters in real life because manufacturers look for stable, roughly symmetric measurements around a target specification. Example 7. A website session histogram has one cluster from 1 to 5 minutes, no observations from 6 to 9, and another cluster from 10 to 15. What feature deserves investigation? Plan. Name the empty interval and consider what separate groups might produce it. Step 1. The interval from 6 through 9 minutes has 0 frequency. Step 2. That interval is a gap. Step 3. The data form 2 clusters on opposite sides of the gap. Step 4. The pattern may reflect 2 user groups, such as quick visitors and engaged readers. Quick check. The graph suggests groups but does not prove their cause. Additional variables should be checked. This matters in real life because product teams investigate multi-peaked use patterns to design different user journeys. Example 8. A histogram uses bins 0 to 10 and 10 to 20 without stating boundary rules. Explain the ambiguity. Plan. Test a value that lies exactly on the shared boundary. Step 1. The value 10 appears to fit both printed intervals. Step 2. One observation must never be counted in 2 bins. Step 3. The display should define intervals such as 0 is at most x less than 10 and 10 is at most x less than 20. Step 4. Clear boundaries assign 10 to exactly 1 bin. Quick check. After boundaries are defined, the sum of frequencies should still match the sample size. This matters in real life because clear bin rules prevent measurement data from being double counted. Example 9. One analyst uses 5-point score bins and another uses 25-point bins for the same test data. Why might their histograms look different? Plan. Consider how bin width controls the amount of detail displayed. Step 1. 5-point bins preserve relatively fine detail. Step 2. 25-point bins combine many distinct scores into each bar. Step 3. Wide bins may hide clusters, gaps, or multiple peaks. Step 4. Both displays can use the same data while emphasizing different structure. Quick check. A fair comparison should use consistent bin boundaries and widths. This matters in real life because education analysts choose bin widths that reveal patterns without making random noise look important. Example 10. Delivery route A is roughly symmetric around 30 minutes. Route B is right skewed with a center near 30. Compare the operational meaning. Plan. Compare both typical time and the risk implied by distribution shape. Step 1. Both routes have a typical value near 30 minutes. Step 2. Route A has balanced variation on both sides of 30. Step 3. Route B has a long right tail, showing occasional much longer deliveries. Step 4. Route B therefore carries greater delay risk even with a similar center. Quick check. A complete comparison should not stop after saying the centers are similar. This matters in real life because logistics decisions depend on reliability and tail risk, as well as average delivery time. Session 5 Recap. Histogram bars touch because the bins cover neighboring numerical intervals. Add every bin frequency to recover the sample size. The tallest bar identifies a modal interval, not an exact mode. Name skew for the direction of the longer tail. Check that every boundary assigns a value to exactly 1 bin, and remember that changing bin width can reveal or hide structure. Quick check. A long tail toward larger values means the distribution is skewed right, even when most observations sit on the left.